Swayam Prabha. Digital India. Educated India.
Okay. Now, if you remember, this is for my example 1 as well as example 2. And I'm going to go look back at example 2 and remember that IJ reads and writes or writes into data location BJ, right? That means the row vertically on the top of the rectangle. Okay. I claim that in this program there is another dependence, and it comes because of memory. Okay. Not only does iteration IJ write into memory location BJ, it overwrites a value that was previously written there by someone else, right? It overwrites the iteration I minus 1J. You agree? Because it overwrites a value, that means that it has to, in any kind of parallelization, we have to make sure that it is not executed before all iterations that read that value have finished. In particular, the east neighbor of I minus 1J is a consumer of that value. You agree? The other consumer is the iteration IJ itself. So, in addition to these dependencies, what happened? Every iteration also depends on, I use the word depends on in quotes, it depends on is northeast neighbor. Okay, why is that? Because the iteration IJ overwrites the memory location that was previously written by iteration I minus 1J, and the iteration I minus 1J plus 1 is a consumer of that value. That iteration must execute before iteration IJ. Do you agree? So in our program, there is this extra dependence that we must account for. Okay. For the time being, we are going to go and ignore them. All right. So now I'm going to switch, because you saw this thing about dependence analysis. I'm going to, like I said, give you the mathematical formulation of that. Okay. And I apologize. I have some slides that are from a while ago, and there are some things there that may seem out of context, but don't worry about it. Okay. But it brings back all the things that I had said previously. Are you seeing my PDF?
Yes.
Okay, then let me go back to the beginning. Okay. I'm going to introduce some notation. Some of it, like I said, doesn't matter, but bear with me. Okay. Right. We have talked about these iteration spaces, and we have talked about the fact that they are polyhedra. Okay. Without going into details, these are sets of indices that satisfy linear or affine inequalities. And in addition, we may have some parameters like n. Okay. So polyhedra have multiple representations. You can think of something as the set of points that satisfy a finite number of linear inequalities, or you can think of it as you have seen sort of in high school geometry or middle school geometry. I say high school geometry because when I teach teach over here, people may not have seen our standard stuff in middle school. But you have this notion of some number of vertices. You do not have an idea of what are rays, and I do not want you to worry about that right now. Okay. If you have a three-dimensional polyhedron like IJN, where n is a special index, you can think of it as a three-dimensional polyhedron, or you can think of it as a two-dimensional polyhedron whose vertices are functions of n. Okay, so here was this, polyhedron that was a line segment, or some. Let me give you a different example. Ij 0 less than or equal to j less than or equal to I less than or equal to m, and j less than or equal to m. Okay, so treat n and m as parameters. Okay, and basically you have, if you just look at 0 less than or equal to I less than or equal to j less than or equal to m, that is a triangle. Okay, but in addition, you have an upper bound on j which is equal to m. All right. So because of that, this is a polytope. There are no, it's not an unbounded polyhedron, it's bounded, and it is parameters by n and m. Okay. If you can visualize this a little bit and try to ask yourself, what are its vertices? The vertices can be functions of n and m, right? Can you imagine this polyhedron? Ignore m and ignore the bound, the upper bound on j, which is given by m. Then it's just a triangle, right? 0 less than or equal to j less than or equal to I less than or equal to m. Are you all there with me? Can you visualize this? Yes? No? You want me to draw it?
Yes, sir. I can see it's a triangle,
Okay.
but I'm not sure about the polytope.
So, well, if it's a triangle, can you tell me what are its corners? It has 3 vertices, right? What are its vertices?
So one is the origin,
One is 0, 0.
and then
I equals j equals m is one of the corners. And n0 is another corner, right?
yeah.
You guys can all visualize it. I'm deliberately trying to do this because, again, in this thing, there are different ways to learn this material. Some people are very geometric and they actually look at things and see that in pictures. Some people are more mathematical and they can see this from equations. And other people can really look at a piece of code and look at and really understand what's going on. All 3 viewpoints are important when we deal with polyhedra. Okay. So I'm trying to go from this mathematical inequality representation to whether you can visualize the vertices. Okay, so 0, 0, n0, and nn are the 3 vertices of this triangle. Okay. And now I have an additional constraint, that is j less than or equal to m, and m is a completely independent parameter. Okay. What happens if m is greater than n? The intersection of the constraint j less than or equal to m and our triangle is just the triangle.
Just the triangle.
Just the triangle. It hasn't changed, right? So then I only have 3 vertices. But what if m is less than n? then it becomes a trapezoid. It's the triangle that is cut at j equals m, that upper bound on j. Okay? The main point I want to make is that its vertices are piecewise affine function of the parameters. And this intuition is very, very important. The set of vertices of a parametric or a parametrized polytope or a polyhedron is a piecewise affine function of the parameters. If a certain inequality is satisfied amongst the parameters, then you have some vertices. Otherwise, you have other vertices, triangle or trapezoid. Okay? This is the key intuition I want you to get from this slide or up to now. Okay? Affine control loops, those are the loop programs that we are analyzing. You have a very good intuition. There is no need to belabor the point. And here's another example. It's now a little bit more complicated than the simple ones that we saw. I'm going to leave these slides for you, and I'm going to, see, if you want to study this in detail, of course you should do that. Okay. What I want you to get from these slides is the main intuition. Okay. So this is a program that solves a triangular system of equalities with a classic forward substitution algorithm. But what it does is really not that important. Okay. You have each assignment statement is given a unique label, like I said, and it represents many instances of operations. One instance for each valid value of points in a surrounding polyhedron. Okay, and this polyhedron for the statement I is parameterized by program parameters. Each operation, that means each value computed by the program, is uniquely identified by a label of the statement and an index point belonging to the polyhedron. When I have, so this last bullet over here is subtle, and it is used to nuance between statements that are in iteration spaces that have different number of dimensions. Okay, there are some statements that are surrounded by one loop. There are some statements surrounded by two loops, etc., as you saw already in this example. Okay, and when you want to compare the relative order of the execution of two such statement instances, what you have to look at is the common loops that surround the two statements. Okay. So when you want to look at some instance of statement S3 and some instance of statement S2, S3 is indexed by I and J, S2 is indexed by I, and you really want to look at the relative orders between I of S2 and the I of S3. The J of S3 does not matter. The J of S3 does not matter because the entire loop, entire J loop that surrounds S is in the statement execution order strictly after the statement S2. It also happens in this case, the textual order. The entire loop is textually after statement S2. Okay? So these are sort of subtle details which it's better to ignore for now. Okay? All right. Even more notation. And then I'll talk about two remarks, because these remarks really link up what we want to do with the data flow analysis. Okay, we talked about the lexicographic order, right? The program execution order is statement S1 at iteration Z1, statement S2 at iteration Z2. Statement S1 at iteration Z1 is executed before statement S2 at iteration S2 if and only if Z1 prime and Z2 prime are the common indices amongst Z1 and Z2. Remember, you're talking about iteration spaces of two different statements. They may be surrounded by some common index. Okay, so Z1 prime and Z2 prime are the common indices. Okay. And on the second branch that I have, there's a typo. That also should be Z1 prime and Z2 prime. Okay. If statement S1 appears before S2 in the program text, then it is that the iteration points are less than or equal to in the lexicographic order. Otherwise, Z1 prime should be strictly before Z2 in order for the Z1th iteration of statement S1 to be executed before the Z2th iteration of S2. Okay? So the lexicographic order is basically the union of polyhedral or union of linear inequalities. Okay? Again, if this statement is not very clear, just be patient, take it on faith for now. If you think a little bit about it, you will get it. Okay? Okay, so the next thing is the lexicographic max or min of two or more vectors is the one that happens later, essentially. Okay, that's why we want to use a lexicographic max or min. Okay? The lexicographic max or min of all points in a polytope is one of its vertices. Again, if this is not intuitively obvious, think about it a little bit offline. For now, just take it on faith. Okay? And we just previously, 2 slides ago, saw that the vertices of a polytope are piecewise affine functions of its parameters. Okay? The other thing is a lexicographic max or min of 2 or more piecewise affine functions is also a piecewise affine function. Again, these are 2 important mathematical properties that if you spend some time thinking about them, you can work them out. Okay? All right, now we are ready to answer the data flow question. Okay? You don't know what a system of affine recurrence equation is. That's what SARE stands for, but don't worry about it. Okay? What we are going to do is to figure out these dependencies between statements and iterations. And remember, we have a collection of statements, and each statement is associated with a point in a polytope. Okay, a polytope is a bounded polyhedron. Again, this distinction is not important, so for this conversation, for this presentation, just imagine that a polytope and a polyhedron are the same. Okay, so now think of this statement like this. Statement label SI. On the left-hand side, you have some variable X, which is being accessed with some function of the loop indices that are visible to the statement and the program parameters. Okay, so my subscript of the function Fi is indicating which statement, and the superscript indicates which reference in that statement. 0 is for the left-hand side reference. Okay? And on the right-hand side, I have many references to many different variables. Each one, however, is going to be some affine function, so subscript I, superscript K, of the surrounding loop indices Z and the program parameters. Okay, and all of these functions, this F sub I, superscript, whatever I, J, K, or whatever, the subscripts and superscript, each of these functions F are affine functions, okay, or linear functions. Like I said, that's synonymous. Which instance or which statement wrote the value of Y that is being read by the zth instance of statement SI? That's our key question. And you want this answer as a function of Z. For different Z, the answer is going to be different. For Z near the boundary, you're going to get something else. For Z sufficiently far from the boundary, you may get something else. Right? All right. Here is the mathematical way of representing this. The answer to this question, which instance or which statement wrote the value of Y being read by the zth instance? And so look, I'm doing this analysis for every reference on the right-hand side. Okay? Well, the first thing must be that it must be some statement in my program that has the variable y on the left-hand side. If it doesn't have a write to y, assuming that there is no aliasing of array variables, if it doesn't even write to the variable y, then that statement cannot even be my producer, right? So there are many statements in my program that have y on the left-hand side, and the candidate, I consider them one by one. Okay? So let's consider some candidate statement Sj, which has y on the left-hand side, and it is writing to memory location f sub j superscript 0. And remember, the statement is some statement Sj, so it has its own indices z prime. And of course, the program parameters, which are common to all statements. All right? So the first two constraints that all my indices must satisfy are the following. First of all, my z must belong to the iteration space of the statement Si, and z prime must belong to the iteration space of the domain of Sj, right? So these are linear inequalities that must be satisfied by these sets of indices. I have two sets of indices, the indices of z and the indices of, or the indices of statement Sji and the indices of statement Sj. Okay? Well, they will be in dependence only if they access the same memory location, the value being read, the memory location being read by the reference in Si must be the same memory location to which that particular instance of Sj wrote. Otherwise, there is no dependence. So f subscript I superscript k of Zp must be equal to f subscript j superscript 0, the right address of the statement Sj, and therefore that function applied to Z prime and P. The other constraint must be that this candidate statement must be something that was executed before the instance Siz that I'm considering. Right? So that's this little triangle. It must have been executed prior to statement S, or the zth instance of statement Si in the program execution order. Okay. Now, if you just look at this set of points Z, Z prime, etc., this gives us a set of points. All points in the program, or all points in the iteration of statement Sj that were executed before this current statement Si, Z, that were executed before and that access the same memory location. Okay? Out of this set of points, the most recent one is the lexicographic max. Okay? Because the lexicographic max amongst these points is really the statement execution order. So the points that satisfy this set of inequalities that I have shown is a union of polyhedra. The lexicographic max, because it's a union of polyhedra and because of the two main properties that I told you, okay, the overall solution is a piecewise affine function of the parameters. Now remember this, I am treating this where Z is a parameter. As Z changes, my set changes. Okay? So the overall, I want to ask the question about which points Z prime in Dj as a function of the particular point Z in Di. So remember when I was thinking of polyhedra and when I told you about sets, parameters are just extra dimensions. So the overall solution of this is going to be a piecewise affine function of z and the program parameters. That's the main takeaway. Okay. So how am I doing for time? It's 9:22. I'm going to go and I'm going to leave these slides as examples for you to study. But here you are really going to encounter a situation where some of the simple things that we did in our first examples don't work. Okay? I mean, they work, but the answer is not that simple. All right, so I'm going to do this analysis of, in statement S3, there is a read on the right-hand side of the array of the scalar variable S. A scalar variable is just simply a zero-dimensional array. Okay? And my question is, which instance of which statement produced the value that is being read in the ijth iteration of S3? Please give me the answer as a function of inj. That's basically the question. And if you are able to stare at this program and by hand work out the answer to my question, you will have, as a human, solved exactly the problem that this dependence analysis seeks to put into a compiler. Okay? All right. There are two statements that write into this. S2 and S3 both write into this variable S, and there are therefore two candidates. My answer could be either S2 or S3. Which of it actually ends up being comes later, and it depends on the program execution order and as I solve the problem. So let us consider each one of those candidates one by one. Okay. So the source of the variable, the reference S in statement S3 is the last one out of these two. Two candidates, two possible solutions, and it is the f1, which is some new function that I'm inventing, f1 of ijth instance of statement S2, or f2th instance of S3. It is actually the later one of those two. That means eventually lexicographic max of these two functions, where each of the functions f1 and f2 that I introduced on the first line are defined as follows. F1, remember, F1 is some instance of statement S2. S2 is a one-dimensional statement. So it is this last of I prime bar ij. So remember, I'm using the vertical bar to separate z prime and z. And remember that I'm going to eventually use the ij in this as parameters. I want this to be, my left-hand side is a function of ij. Okay? So it is the last I prime such that I prime belongs to D2, ij belongs to D3. What about this constraint that I had 2 slides ago? The memory location being accessed is the same. That is vacuously true because my array variable is a scalar variable. Both of the statements, all statement instances that write into S, write into the same memory location because S, in our case, happens to be a scalar. So that equality constraint went away. And all you want is S2 I prime occurs lexicographic, precedes S3 ij in the execution order. Okay. And similarly, the F2 function ij is some iteration of statement S3, the I prime j primeth iteration such that I prime j prime belongs to D3, ij belongs to D3, and I prime j prime happens before ij. Okay. Now, what we are going to do is that in the first function, we're going to look at the inequalities that we get out of that last execution order. Remember, I primeth iteration of statement S2 is executed before the ith iteration of statement S3, and this happens if and only if I prime is less than or equal to I. It happens less than or equal to comes because the statement S2 is textually before statement S3, right? So even if I prime equals I, the I primeth iteration of S2 is executed in the program execution order before the ijth iteration of statement S3. If you think back at the program the code that I showed you and I pointed to you before, that's what happens. Okay, so the nuanced view of happens before in the execution order can be like I just did in this example, be split into linear inequalities. Okay, and we will see soon the idea of the similar linear inequality that happens in this two-dimensional example of F2, but later. Okay, before that, let us simplify this function F1. Okay, that triangle now simply becomes I prime less than or equal to I, right? So we have the constraint that I prime belongs to D2, Ij belongs to D3, and I prime belongs to I. If you simplify those a little bit, you are looking at all the instances of the last instances of all the points I prime, such that you have all these linear inequalities to be satisfied. And out of those, the last one is the last point in a line segment, and it happens to be one of the vertices of these line segments, and the vertex of that line segment is I. Okay? If you draw out this visually, you will see that. What you have obtained is that the answer F1 is a function of I, and you got it that way because you treated Ij as parameters. Okay? So, now if you look at this function F2, where we are looking at the execution order of I prime j prime compared to Ij, it is that I prime j prime is executed before iteration Ij if either I is strictly greater than I prime, or I prime equals I, and then j prime is strictly less than j. It is the disjunction of two sets of inequalities. And if you think a little bit about it, that is what it leads to the union of two polyhedra. In this case, two, but in general, union of polyhedra. So the lexicographic order among indices, the execution order, can be broken up into the union of, in fact, the disjoint union of polyhedra. Okay? And again, I don't expect you to go get all the details of all of this right away. I just want to make sure that you get the big picture intuition. All right? So when you go through this, the math gets more and more complicated. Okay, and I'm not going to go into the details. And eventually, you get this function F1 and F2. Okay, where did that go? All right, and then you combine them because this is the over two disjoint unions, and therefore you take the last of these two, etc., etc. And everything that I said about the properties in the machinery before are going to be useful. And eventually, this is what F2 simplifies to. And you see the corner cases. If I equals 2 and j equals 1, it is bottom because there is no instance of statement S3 that produced the value. If I equals 1 and j greater than or equal to 3, then it is I minus 1, j minus 2. Otherwise, sufficiently far from the boundaries, it is I, j minus 1. Okay? And now you take the last of these two solutions, and that becomes some piecewise affine function of I and j. Okay? So, I am going to stop this digression or this for now, and I'm going to take questions because we are at 9:30, so we've done about 35 minutes. Is the big picture intuition clear?
Yes, sir. Can you please explain the interpretation of F and its subscript and superscript. I lost track of that.
Okay, that is easy. That part is. Did I stop sharing, or are you still seeing my PDF?
No, sir.
You're not seeing my PDF, so let me. The F and its subscript really comes from the syntactic analysis of your program. So what you do is basically you construct an intermediate representation of your program, and you have some representation of the loops.